It is a terminology in chemistry of life. It is an important term in chemistry, in nuclear chemistry and nuclear physics as well, since it characterizes the material of life. It characterizes the reaction. It is highly specific. It has one value for one material, one value for one reaction. That is the one we need the study of this in chemical kinetics, nuclear physics or nuclear chemistry. Let us understand the definition of half-life. Here only the definition is here. It is the time taken for half change in the concentration. It is the duration in which, the time duration in which exactly half of the reactant has changed into product. The remaining half remains. The time is called as half change. It is called time for half change as well. The symbol is T off. The definition, that is, what is the time required by the reaction to complete half of the reaction, half of the concentration of the reactant what you have taken. Let us look into the concept, that is concept of half-life in the form of mathematics, in the mathematical form. These are the usual notations. A gives rise to a product. This I already told you, when T equals 0, commencement of reaction, the initial concentration of the reactant is A, small a. After time T, sometime, the concentration of the reactant remaining is A minus X. X is the concentration change. X is the concentration of the reactant change in the product. Concentration of the reactant disappear. That is why. Now let us see the half-life. When X equals A by 2, exactly A by 2, half of the initial concentration. The change in concentration is half of the initial concentration taken. The time is now is called as T off. It is half-life for this change. This half-life is related to the rate constant, expression of rate constant. So we have the rate constant for three different orders. Let us see the relationship. What is the relation between the rate constant and half-life in three different orders of reaction? Recall the mathematical expression of all the three rate constants. That is the rate constant for zero order, rate constant for the first order, rate constant for the second order. Let us put these values into the expression and simplify what we get. That's all I have done. Into this equation, I put this. When x equals a by 2, t equals half. That is, x is a by 2, t is t half. Simplify. That is a to half. T half is equal to a by 2k. Half-life of zero order reaction is depending on the initial concentration. Is proportional to, directly proportional to this 2k. 1 by 2k is a constant, of course. So that's the equation you get. Half-life of a zero order reaction is depending on the concentration, initial concentration. I'll tell you later. Let us see what we get after simplifying when you put these values into this equation. X, t. Put them into this. T equals t of x equals a by 2. Simplify. X equals a by 2, t equals t by 2. This you know a minus a by 2 is half a by 2, and simplify this a cancels 2 goes to numerator. 2.303 into log 2 is 0.693 T off in the numerator. So what is off life? T off is equal to 0.693 divided by K. Look at this, very important. This expression is not containing the initial concentration. This off life is not depending on the initial concentration. Is independent of initial concentration, constant, but is depending on the initial concentration. There is an expression for off life and rate constant for the first order. The expression for off life, rate constant, this is for rate constant for zero order. Don't confuse, all K only. First order, second order. Let us see what you get in this second order. The second order. Let us put these values into this. Same values. Simplify. You have put x equals a by 2, t equals 1 by 2, t off. This is a minus a by 2 is a by 2. 1 over a by 2 is 2 by a minus of 1 by a. Simplify. Take calcium and simplify. You get 1 by a. 2 minus 1, 1 by a. So T off is equal to 1 by Ka. Look at carefully this equation. This is off life of second order. It is function of initial, not numerator, function of initial concentration. Of course, related to, but inversely. It is depending on initial concentration, but inversely related. Look at the differences. These are the differences. Off life for the second order, relations between off life and rate constant of second order, relations between off life and rate constant of first order, relations between off life and rate constant of zero order. These equations, remember, because they set a problems on these equations for solving. And let us see in details what is this. Off life concentration equation, this is for zero order. Off is equal to 1 by 2K times the concentration of A. Off life is directly proportional to, directly related to initial concentration. Higher the concentration, higher, same reaction. Higher the concentration, higher the off life rate. Lower the concentration, lower the off life. That is what the equation says. But equation 2 for the first order, very interesting. Half life is equal to, is a constant, numerical value divided by constant. Constant by constant is a constant. Half life is a constant. That means it is always a constant value, one value for first order reaction. That is for that particular fraction. That means it is not depending on the concentration. Whichever may be the initial concentration, half life remains same. So let us look into details of this. Suppose half life of the first order reaction, I have taken just one simply an example of this, 2.6 minutes. In this duration, half of the reactant concentration change. If you have taken initial concentration is 1 molar, 1 mole per dm cube, for a change of 1 into half mole, time taken is half life. If you have taken 2 molar concentration, change into exactly half of this is 1 molar. If you have taken 0.5 molar concentration of this, changing this into this is 0.25, half of this. So the change in the concentration is half. Change in the concentration is 1 molar. Change in the concentration is 0.25. Look at the differences. That is change. Magnitude of reactions are different, but half change. Time taken for this, all of same. Here half a mole change, here 1 mole change, here 0.2 mole. But time taken is, that is the actual meaning hidden in this equation. It is independent of the initial. If you have taken 10 molar, 10 into 5 molar, here 5 mole change, but time taken is 2.6. That is the, what is that importance it is in this equation. Half life is constant. And the next equation, the third one is Half life is equal to 1 by k. The same thing is written 1 by a. Half life of second order is what is that? Concentration dependent. Initial constant, but is inversely related. Inverse. It means higher the concentration, lower the half life, or vice versa. Lower the concentration, higher the half life. The difference here, higher the concentration, higher the half life. Higher the concentration, lower the half life. Values are related. So it is, what is that? Half life is a function of concentration but inversely related. That is what the explanation is that. Looking at this, all these mathematical equations, what you have derived, this is the one we have derived, another one. We can have a generalized, what is that? We can make some generalization over here. Looking at these equations, it shows that half-life is directly proportional to a to the power of 1 minus n. A stands for initial concentration, n stands for order of the reaction. Let us look into this for the same relation. That is generalization. I am taking the function. Half-life is a function of initial concentration to the power of 1 minus exponential of 1 minus n. Let us write this. Half-life when n equals 0, a to the power of 1 proportional to a, that is same as 0 order, proportional to initial concentration. For a first order when n equals 1, 1 minus 1 means 0. A to the power of 0 means 1. 1 is a constant. Half-life is constant for n equals 1. First order. The same thing, what is that? That is in another way, that is in generalization. For a second order, put n equals to 1 minus 2 is minus 1. A to the power minus is 1 by a. Half-life is inversely proportional to initial concentration like this. But similarly, generalization, if it is third order, half-life proportional 1 by a square, because when you put 3, a to the power of minus 2, that is 1 over a2, inversely proportional to a square concentration of initial. That is generalization, because this equation you have to remember. All this equation to be remembered for this. This equation is a must for solving the problems. But this is one more equation, general equation. T of is always proportional to a to the power of 1 minus 1. This is the one we require half-life concept in the determination of order of reaction. There you see that the generalization. So thank you very much.